A thin red star fills the frame, quiet, steady, almost too small to carry so many hopes. Then the light dips. Not by much. A shallow bite taken out of starlight. The signature of an exoplanet crossing in front of its star. And then another dip. Another crossing. Another shadow. It should line up. It should repeat. It should behave. But the shadow doesn't hold still. The case opens on a single, stubborn phrase. Shadow on TRAPPIST-1e shifted again in Starspots versus signal what we know. That shifted again is the whole problem packed into 3 words. A change over time, small enough to miss, big enough to matter. The kind of change that can turn an atmosphere story into a cautionary tale. We're here for one question, plain and sharp. What exactly shifted? And what does that shift mean? Changes when the shadow shifted again. We changes when the shadow shifted again. We have 2 competing explanations that feel almost like characters in conflict: planet atmosphere versus star contamination. Signal versus artifact. Start with what a transit gives us at its simplest. A planet crosses the face of its star and blocks a fraction of the light. The dip arrives, reaches its deepest point, and rises again. The curve is a shape, a timing, a depth. The exoplanet becomes real through repetition, through the same shadow returning on schedule. So when we say shifted again, we're not talking about poetry. We're talking about measurable behaviors that can move. The timing can slide, arriving a little early or late, not because the planet changed, but because our prediction drifted or our sampling missed the exact bottom of the dip. The depth can change, looking like the planet got bigger or smaller. The shape can warp, suggesting something about the path across the star or the surface the planet is crossing. And crucially, for atmosphere interpretation, the shadow can become different at different colors of light. Chromatic, uneven, suggesting gases or haze. Or suggesting the star is not the clean uniform lamp we wish it were. This is where the title's tension lives: Starspots versus signal. It's not a philosophical debate. It's a confounder test. It's the difference between reading a planet's atmosphere and reading the star's skin. TRAPPIST-1e is the named target in the title, and we keep our eyes on it. In the abstract, you can talk about exoplanets like distant marbles. But this is a specific world with a specific kind of parent star, a small cool star, where stellar activity is not a footnote. It's an active ingredient. Here's the first evidence moment, and it's almost unfair. In its simplicity, the light curve. The planet's shadow changes. That change could be the planet, or it could be the stage. Imagine trying to judge the size of a coin by the shadow it casts, while the light bulb flickers and the table surface is mottled. You can measure precisely and still be wrong. That's the unease in modern exoplanet atmosphere. Work detection versus interpretation. We can detect the transit. The question is what the transit means. When viewers hear shadow, they picture a crisp silhouette. But our silhouette is made of photons, counted and compared. A transit is starlight filtered through geometry, and sometimes filtered through an atmosphere. That's why these shifts matter so much for the search for signs of life. Not because a shifting shadow is itself a biosignature, it's not, but because every future claim about a biosignature depends on the same fragile chain of inference. And that chain can be fooled. Star spots and bright stellar patches faculae can change the apparent depth and shape of a transit. If a planet crosses a darker patch, it blocks less additional light than expected. If the star's overall surface is dimmer or brighter than our model assumes, the planet's shadow can look deeper or shallower. This is contamination in its most insidious form, the star masquerading as the planet. If the shadows shifted again, behavior tracks with signs of changing stellar surface patterns, rotation phases, active periods, subtle changes from one epoch to the next. Then the cleanest explanation is stellar contamination, not a suddenly changing planet. But inference is not victory. It's a ranking of likelihoods. And still, we can't dismiss the planet outright. Not if we're being honest. A planet's transit can look different with wavelength if its atmosphere scatters or absorbs starlight differently at different colors. That's the doorway to atmospheric chemistry, to spectroscopy, to what is this air made of, and eventually to the careful, guarded search for biosignature-relevant patterns. But we are not allowed to walk through that doorway until we have checked whether the star forged the key. So we bring the tension into plain language planet atmosphere versus star contamination, signal versus artifact, model fit versus the messy reality of a living star. Now we name the first concrete confounder that can manufacture the illusion of a shift without the planet changing at all time. Variability versus sampling, because sometimes the shift isn't in the sky. Sometimes it's in our coverage. A small number of transit's gaps in observing and imperfect baselines can make a transit look like it moved or changed when we simply didn't capture the same portions of the curve with the same precision each time. The transit may be stable, but our sampling isn't. Ephemeris errors, small drifts in predicted timing can compound that impression. The shadow shifted again can be an honest consequence of limited windows, not a physical transformation of TRAPPIST-1e. This matters because it dictates the next move. If the shift is an artifact of sampling, the fix is not a better story, it's better discipline. More repeated observations, better alignment. Stronger checks that the change is not a byproduct of how we looked. And in this episode, we don't get to skip that discipline, because the title promises something else too, what we know. Not what we hope, not what we want. What we know, what we infer, what we speculate, and where each category can collapse under a confounder. So we end this opening movement with a precise, ominous calm. TRAPPIST-1e's shadow appears to have shifted again, and the shift could be telling us about an exoplanet atmosphere, or it could be the star's surface, writing false letters into the record. The only way forward is to interrogate the measurement itself. Next, we step into the machinery of inference, the data mode that turns a shadow into an atmospheric argument, in the places it can be fooled. The light arrives like a confession made in whispers. Not the whole confession, not the full story, just a thin slice of starlight collected, compared, and held up to the harshest question exoplanet science can ask. Is the planet leaving a trace in the light? Or are we only seeing the star's own changing face? This is the section where we earn the right to interpret anything at all. How we know transit spectroscopy for TRAPPIST-1e signal versus starspots. The title thread is still tight in our hands. The shadow shifted again, and the entire credibility of the signal depends on whether we can keep starspots from writing the ending. So what do we actually measure? We measure starlight before the transit, during the transit, and after. We measure it not just as a single brightness number, but as brightness spread across wavelengths. That's the key move. We are not trying to see an atmosphere directly. We are trying to detect whether the transit shadow is slightly deeper at some wavelength than others. This is the idea that makes the modern atmosphere hunt possible, and also makes it so easy to fool ourselves. Here's the evidence moment, simple and brutal. We take in transit light and out of transit light and subtract one from the other. A difference that's small can become the entire story. If certain wavelengths dim just a little more during transit, one interpretation is that the planet has an atmosphere that absorbs or scatters those colors more strongly. This is the logic behind transmission spectroscopy. The atmosphere acts like a thin ring. At wavelengths where gases absorb, the planet appears effectively larger because the atmosphere blocks a tiny extra portion of the star's light. The shadow deepens in those colors. That's the pathway from a shadow to an atmospheric claim. But it has hidden assumptions, and the biggest assumption is the one we rarely get to keep, that the star is a clean, stable backlight. On TRAPPIST-1e, the star is not a blank screen. It is a surface, textured, evolving, sometimes moody. In the title's own language, starspots versus signal. Star spots and bright patches don't just change the star's brightness, they change its color. They change the spectrum, and that creates the central tension pair, in plain terms, planet atmosphere versus star contamination. The same kind of wavelength-dependent change we hope is atmospheric can also be written by the star. Stellar spots and faculae can introduce chromatic effects, wavelength-dependent changes that mimic atmospheric slopes or mute real features. If part of the stellar surface is cooler or hotter than the average, the baseline spectrum we assume is wrong. Then, the transit looks like a change with wavelength, even if the planet has no meaningful spectral imprint at all. That's contamination in its most treacherous form. It doesn't look like noise. It looks like a pattern. So how do we keep the method honest? We don't do it with a single transit. We do it with repeatability and cross-checks. If the shadow shifted again in one visit, we ask whether it shifts again in the same way in another. If the spectral shape changes from one transit to the next, we ask whether that change lines up with signs of stellar activity. Because a real atmospheric signature should not behave like a fickle mood unless we have independent reasons to believe the atmosphere itself is changing. And our outline gives us no right to claim that. So we treat variability as suspect until proven otherwise. This is where retrieval enters, not as a magic word, but as the formal act of translating data into probabilities. We take the measured transit depths across wavelengths and ask what atmospheres could produce this, what stellar contamination patterns could produce this, what combinations fit. And we don't get to pretend the answer is a single curve. It's a space of possibilities shaped by model assumptions. Retrieval and modeling turn spectra into atmospheric statements, and every step includes assumptions that can amplify uncertainty. The retrieval can tell you which scenarios are consistent with the data, but it cannot guarantee that the data represent the planet alone. That's why multiple transits matter so much in a case where the shadow shifted again. Each additional observation is not just more data. It's a test of stability, a test of whether the same spectral fingerprint returns under different stellar conditions, or whether the fingerprint changes because the star changed its mask. And we allow ourselves a narrow, carefully labeled possibility if, after correction and careful accounting, a residual wavelength-dependent pattern persists across epochs. Something that stays put when the star's activity changes, then it becomes a candidate constraint on atmosphere or haze. Not a biosignature, not a sign of life, a constraint, a boundary placed on the unknown. But the method has another enemy besides the star. The second confounder we must name here explicitly, concretely, is instrument systematics. Because we are measuring tiny differences. Instruments drift, detectors have quirks, wavelength solutions can slip, thermal conditions can shift, instrument systematics, thermal stability issues, detector effects, wavelength calibration problems can create apparent features that look atmospheric. They can also create apparent changes that feel like the shadow shifted again when in reality the instrument's response shifted. So an honest analysis doesn't just correct the data once and move on. It builds redundancy, Confidence increases when different analysis pipelines converge, when injection and recovery tests show we can detect a signal of the claimed type without manufacturing it, and when multiple visits tell the same story. The method demands skepticism as a feature, not a mood. And the title demands the same. What we know is not just content, it's a stance. So we arrive at the answer to this section's key question: transit spectroscopy measures wavelength-dependent changes in the transit shadow, which can be consistent with an exoplanet atmosphere, but the method is fundamentally vulnerable to stellar contamination and instrument systematics. The signal versus star spots tension is not optional. It is built into the measurement itself. Now the story has a pivot point. If the method can't separate the planet from the star on its own, then the next move is to change the viewpoint. We stop treating the star as a backdrop and start treating it as a source of structure, a writer of false patterns. We look back at TRAPPIST-1e's shifting shadow and ask a colder question: what if the planet is steady and the star is the one doing the talking? The star turns slowly, quietly, like a stage rotating beneath a fixed spotlight. And as it turns, the surface is never the same twice. Dark regions, bright regions, subtle textures that we can't resolve as an image, only infer as consequences. In the data, that texture becomes a voice. Sometimes it sounds like an atmosphere. This is the moment we deliberately change our posture. Change of perspective. When star spots write the story and the shadow shifted again, we stop assuming the planet is the source of the mystery. We assume the planet is steady until proven otherwise, and we interrogate the star as the moving part, because the title doesn't let us forget what's at stake. Shadow on TRAPPIST-1e shifted again, star spots versus signal, what we know. The words "shifted again" are not a flourish. They are a warning. Something changed between observations. And in exoplanet atmosphere, work a changing star is often the simplest explanation. So here's the key question, set in plain language. How can the star's surface patterns make an exoplanet atmosphere appear to change when it hasn't? We begin with what is established. Spot and faculae coverage can change with stellar rotation and activity cycles. Even if the star's overall brightness looks roughly stable over a night, the distribution of bright and dark regions across the surface can shift. The star is not a uniform disk. It is a patchwork. Now bring the planet's transit back into that patchwork. A transit is not just a planet crossing a star. It is a planet crossing a specific path across that star, what astronomers call the transit chord. We don't need the jargon to feel the implication. The planet is sampling the star's surface like a needle moving across a record. If that needle crosses different terrain on different nights, the music changes. Here's an evidence moment that doesn't require numbers. Take the same planet, keep its size and orbit fixed, and change only the star's surface pattern. The resulting light curve can change its depth, its shape, its apparent color dependence. The shadow can shift without the planet doing anything at all. That's not a philosophical possibility. It's the reason star spots versus signal is a permanent tension in this niche. Dark spots and bright faculae can alter the observed transit baseline and distort the transit depth and shape. If the star is dimmer overall because of spots, a given amount of blocked light can look like a larger planet. If the planet crosses a spot, the transit can look shallower in that segment. The curve bends. The silhouette seems to misbehave. And then comes the part that directly threatens atmospheric interpretation. The star's heterogeneity can be chromatic. Different colors of light are affected differently. That means the same dataset feature we might interpret as an atmospheric slope or muted absorption could be written by the star's surface temperature contrasts instead. In other words, planet atmosphere versus star contamination isn't just about total brightness. It's about color, about spectroscopy, about whether the atmosphere we think we're measuring is actually the star's own spectral texture. Now we sharpen the inference that the outline allows us to make. If the shifted again behavior aligns with the star's rotation phase or other indicators of stellar activity, stellar contamination becomes the leading explanation, not because it's convenient, because it's physically expected on these stars, and because it naturally produces variability from one transit to the next. And we keep our honesty intact. This is inference, not proof. We are ranking explanations. Chromatic shifts changes that look stronger at some wavelengths can arise from stellar heterogeneity, not just from an exoplanet atmosphere. That means a wavelength-dependent transit signal is not automatically an atmospheric detection. It is a clue that must survive a cross-examination. That cross-examination is the spine of this episode's signal versus artifact. Now we allow one carefully fenced line of speculation because the planet is not forbidden to have an atmosphere. We're simply forbidden to pretend we've isolated it. A stable, truly atmosphere-driven signature should be repeatable across epochs after correcting for plausible stellar surface models. If something persists while the star's activity changes, that persistence begins to look less like contamination. But we immediately acknowledge the trap. The correction itself depends on modeling the star. And that leads directly to the confounder this section must name. Not vague uncertainty. A concrete mechanism that can steer us into the wrong conclusion even when we're trying to be careful. Retrieval priors and model assumptions. Because once we decide the star matters, we have to model it. And models are choices. Different assumptions about the star's spot coverage, temperature, contrast, and distribution can change what we conclude about the planet's atmosphere. The retrieval can explain the same spectrum with different combinations of star contamination and atmospheric properties. The result can look decisive while being conditional. This is where the slightly ominous tone becomes earned. Not because the universe is hiding life from us, but because it's easy to hide our own uncertainty behind a clean-looking fit. So we hold the tension pair up in one sentence that feels like a verdict, but isn't model fit versus reality. A model can fit beautifully and still be wrong if it's fitting the star's unmodeled complexity. And we return explicitly to the title thread, because this section is the title thread inverted. When we say TRAPPIST-1e's shadow shifted again, we are also saying the star may have changed its face. The signal may be the star spot pattern leaking into our spectroscopy and masquerading as an exoplanet atmosphere. That is the case we have to build and the case we have to try to break. Now we're ready for the next movement. Because once you accept that both stories can fit planet atmosphere and star contamination, you need a discipline stronger than preference. You need a checkpoint, a place where we decide what counts as know, what remains infer, and what must stay speculate. We move forward with a colder question than before. If the shadow keeps shifting, what can we responsibly conclude about TRAPPIST-1e at all? The curve sits on the screen like a thin scar, quiet, precise, and not quite trustworthy. It's tempting at this point to choose a side, to decide the shadow is a planet speaking or a star deceiving, to take the most elegant story and let it harden into certainty. But this is where the episode must do something rarer than revelation. It must stop. It must look at its own limits. Cosmic checkpoint. TRAPPIST-1e. After the shadow shifted again. Limits of inference. Not cosmic in the sense of grand distances or ancient galaxies. Cosmic in the sense that even here, close to the data, close to the math, we run into the edge of what inference can honestly claim. The key question is blunt after testing starspots, systematics, and modeling degeneracies. What can we responsibly say about TRAPPIST-1e's atmosphere? And we keep the title thread intact, because this checkpoint exists for the title's promise. Shadow on TRAPPIST-1e shifted against starspots versus signal what we know. The phrase "what we know" is not decoration, it's a boundary line. So we make a scoreboard, not of winners, but of survivals. What survives the confounders? First, what we can place in the category without stretching it. A changing transit signature can be produced by stellar contamination and/or instrument systematics without any real atmospheric change. That statement isn't cynical. It's the baseline reality of this kind of measurement. If the shadow shifted again, there exists a fully physical explanation that lives entirely on the star or in the instrument. That is knowledge in the strict sense. It's a known pathway to false patterns. Now, what we can infer, carefully conditionally based on the outline's logic, the most responsible, best current conclusion is the one that remains consistent across multiple epochs and independent diagnostics of stellar activity. In other words, if the signal is real, it should not behave like the star. It should persist when the star's surface changes. If the signal is contamination, it will often move with the star's own variability. This is the checkpoint's first tension pair, stated plainly, signal versus artifact. The data can be precise and still be ambiguous. Precision is not immunity. Here is an evidence moment we are allowed to show without inventing numbers. The act of cross-examination itself. We take the transit and ask 3 questions, each designed to catch a different liar. Does the pattern repeat across transits, or does it morph as the star's activity changes? That targets stellar activity as a confounder. Do independent calibration and reduction approaches converge on the same spectral shape? Or do features appear and disappear with pipeline choices that targets instrument systematics and the risk of hidden calibration? Drift. Do different plausible models, different model assumptions force radically different atmosphere stories from the same data? That targets retrieval degeneracy, the idea that multiple explanations can wear the same mask. None of that is a flourish. It's the path to what we know. Now we state the best current logic the outline permits again as inference. If the signal weakens or changes with stellar indicators, the balance tilts towards starspots and faculae as the driver of the shifted again behavior. The word tilts matters. It's not a final verdict. It is an honest update of likelihood given a specific confounder test. And we carve out the narrow speculative corridor, because science is allowed to be curious as long as it labels its curiosity. If a residual wavelength pattern persists after robust stellar and systematics modeling, it becomes a candidate constraint on atmosphere or haze. Not a discovery of life, not a biosignature claim. A constraint, meaning a limit on what the atmosphere could be or how strongly it imprints on the starlight. Now we face a different kind of limit, the kind that remains even if every calibration is perfect and every spot model is careful. This is the checkpoint's necessary confounder, named explicitly clouds and hazes degeneracy. Because even a clean transmission spectrum can refuse to confess. Flat or muted spectral features can mean there are no strong absorption signatures within the measured band. But they can also mean that clouds or hazes are masking features that would otherwise appear. The same observed spectrum can be consistent with very different atmospheric realities. This is the heart of degeneracy detection versus interpretation, again, but now on the planet side, not the stars. And this is where the ominous tone becomes quiet and earned. You can do everything right and still arrive at a conclusion that is bounded, partial, probabilistic, For viewers, the translation is simple. The universe doesn't owe us clarity. We must earn every step towards signs of life, and part of earning it is admitting when the measurement cannot uniquely identify what's in an exoplanet atmosphere. The checkpoint is not a retreat. It is the only way to keep future biosignature talk from becoming a false positive factory. So what do we know right now in the strict language the title demands? We know the shadow shifted again, and we know that stars and instruments can create shifts. We infer that repeatability and independent diagnostics are the route to a best current conclusion, and we speculate only lightly that a persistent residual could someday inform an atmosphere constraint. But we do not claim life. We do not claim a definitive atmosphere composition. We do not pretend the data has said more than it has. And now, we pivot toward the ending. Because this checkpoint doesn't just tell us where we are. It tells us what we still owe the story, one measurable unknown that decides whether TRAPPIST-1e's atmosphere is readable at all, or whether the star's moving mask will keep rewriting the shadow. We go from inference to the final burden, naming the missing measurement that would settle the argument. The room is dark, the screen is bright, the star is a soft ember, and the transit curve so thin, so confident, hangs there as if it wants to be believed. But belief is not the currency here. Measurement is. This final movement is not a reveal. It's an after-image. Limitation heavy. The shadow's after-image, what we still don't know about TRAPPIST-1e. The tone tightens not into despair, but into precision, because the title's promise still stands. Shadow on TRAPPIST-1e shifted again, Starspots versus signal, what we know. If it shifted again, the last honest act is to say what that shift still prevents us from concluding and what specifically would resolve it. The key question is simple, and it doesn't flinch. What single, measurable uncertainty most blocks atmospheric interpretation, and what future data would reduce it? We keep the story inside the micro niche. This is about exoplanet data, becoming inference meeting uncertainty, and uncertainty shaping the meaning of the search for signs of life. So we begin with the core limitation stated in the plainest terms. Stellar heterogeneity can dominate the era budget for small planets around active stars, limiting atmosphere detectability. That's not a pessimistic slogan, it's a physics and measurement reality. When the star's surface is patchy, cool, spots hot faculae, its spectrum changes in ways that can masquerade as or drown out a planet's atmospheric imprint. It means the shadow is not only the planet's shadow, it is the planet's shadow projected onto a moving screen. Here's the evidence moment, but it's an evidence moment about method and restraint. The same dataset can support multiple stories. A measured wavelength-dependent transit depth can be read as spectroscopy of an exoplanet atmosphere. Or it can be read as contamination stellar activity leaking into the measurement. Or it can be a mix. And without pinning down the star's surface, those interpretations can trade places. That's why Starspots versus signal is not a debate we settle with rhetoric. We settle it with a specific missing measurement. Now we name it exactly as the outline requires. This is the measurable unknown that still blocks the case. The spot/facula, coverage fraction and temperature contrast along the transit chord, stellar heterogeneity where the planet actually crosses. Not the star in general, not the star on average, the star along the path the planet samples. This is the unknown that decides how easily the shadow can shift it again without TRAPPIST-1e changing at all. And now we keep our honesty tags tight. More transits improve statistical power, but only if stellar variability is tracked and modeled, not averaged away blindly. More repetition is not automatically more truth. if the star's mask changes from transit to transit stacking, can blur reality into a misleading average. Independent monitoring of stellar activity can convert some mystery shifts into explainable contamination. If we can tell what the star was doing at the time of each transit, how its surface was configured, how its spectrum was leaning, then the planet's contribution can be isolated more cleanly. And we allow one carefully bounded speculation because it points forward without inventing outcomes. With broader wavelength coverage and repeated epochs, we may separate stellar chromatic effects from genuine atmospheric patterns, enabling stricter constraints on TRAPPIST-1e's atmosphere. Not certainty. Constraints. The kind of constraints that would be prerequisites for any future conversation about biosignature claims on worlds like this, because false positives begin at the star. That's the larger meaning. Stated quietly, the road to biosignatures is paved with confounder control. If we cannot control stellar heterogeneity, then any future pattern that looks lifelike risks being a mirage. And if we can control it, if we can measure it, then the shadow stops being a Rorschach test. The limitation-heavy truth is that the universe has not refused to speak. It has spoken in a language that includes the star's complexity. The burden is on us to translate without hallucinating. So we return to the title. One last time. In the same sober cadence, the shadow on TRAPPIST-1e shifted again. That shift does not prove an atmosphere. It does not disprove one. It proves something harder and more useful, that the star can forge convincing signals, and that what we know is defined by what survives that forgery. 2 sentences of calibration, no more. On Earth, we can separate air from ground because we can stand inside the system. In exoplanet science, we do it from starlight alone, so the star's surface becomes part of the atmosphere story, whether we like it or not. We end with the measurable unknown held steady in frame spot, and faculae coverage fraction and temperature contrast along the transit chord, stellar heterogeneity, quantified, not guessed. That's what future data must resolve, so we can finally say whether TRAPPIST-1e's shadow is carrying a readable atmospheric imprint, or only the star's moving handwriting. And with that, the episode closes, not on certainty, but on a clean, testable question, because that is the only kind of hope the data can justify.